For millennia, humans have gazed up at the night sky in wonder, captivated by the twinkling lights that dot the darkness. We've observed the celestial ballet of the planets, the moon, and the stars, each moving in a dance that has fascinated us for generations. These cosmic objects have sparked our curiosity and inspired countless myths and legends, shaping cultures and civilizations throughout history. But it's only in recent centuries that we've begun to truly understand the laws that govern their movements, thanks to the advent of telescopes and the scientific method. Planetary motion, the way planets orbit around their stars, is a fundamental concept in astronomy, revealing the intricate dance of celestial mechanics. It's a story of gravity, inertia, and cosmic forces that have shaped our universe since its inception, a tale written in the fabric of space and time. By studying planetary motion, we gain insights into the formation of our solar system, the nature of gravity, and the vastness of the cosmos, unlocking secrets that have eluded us for centuries. Understanding planetary motion allows us to predict celestial events, launch spacecraft with precision, and explore the possibility of life beyond Earth, pushing the boundaries of human knowledge and capability. It's a journey that takes us from the familiar ground beneath our feet to the farthest reaches of space, expanding our horizons and challenging our perceptions of the universe. As we delve into this fascinating subject, we'll uncover the elegant laws that govern the movements of celestial bodies, laws that are both simple and profound in their beauty. From the early geocentric models of the universe, which placed Earth at the center, to the modern understanding of elliptical orbits and gravitational waves, our knowledge has evolved dramatically. We'll trace the evolution of our knowledge and marvel at the intricate workings of the cosmos, appreciating the vast and complex universe we are a part of, and the endless possibilities it holds for future exploration and discovery. In the earliest attempts to make sense of the heavens, humans placed Earth at the center of the universe. This was not just a random guess, but a conclusion drawn from careful observation and the limited knowledge available at the time. This geocentric model, with its intuitive appeal, held sway for centuries. It was a model that made sense to the people of the time, fitting neatly with their everyday experiences and observations. It's easy to see why. From our vantage point on Earth, it appears as if everything revolves around us. The sky seems to be a dome with stars affixed to it, rotating around a central point. The sun rises in the east, travels across the sky, and sets in the west. This daily journey of the sun reinforced the belief that Earth was the center of all celestial motion. The stars seemed to follow a similar path. Night after night, they appeared to move in a grand, predictable dance across the sky. The geocentric model was championed by the ancient Greek philosopher Aristotle. His influence was so profound that his ideas shaped scientific thought for many generations. His ideas, later incorporated into the Ptolemaic system, became the accepted model for over 1,400 years. This system was detailed and complex, reflecting the sophistication of ancient Greek astronomy. This model posited that Earth was stationary, and the sun, moon, planets, and stars all moved around it in circular orbits. The elegance of circular motion was thought to reflect the perfection of the heavens. To account for the observed retrograde motion of planets, Ptolemy introduced the concept of epicycles, smaller circles within the planet's larger orbits. This ingenious solution allowed the model to match observations more closely. While the geocentric model provided a reasonably accurate way to predict the positions of celestial objects, it was based on flawed assumptions. The insistence on circular orbits and the centrality of Earth were its major weaknesses. It was a model that attempted to fit observations to a preconceived notion, rather than allowing observations to guide the development of a more accurate model. This approach limited its ability to adapt to new data. The geocentric model, despite its limitations, played a crucial role in the history of astronomy. It was a stepping stone that led to more accurate models and a deeper understanding of the cosmos. It provided a framework for observation and measurement, laying the groundwork for the scientific revolution that would eventually overturn it. The tools and methods developed during this period were invaluable for future astronomers. It serves as a reminder that even incorrect theories can advance scientific understanding. By challenging and refining these early ideas, scientists were able to build a more accurate picture of our place in the universe. The 16th century witnessed a profound shift in our understanding of the universe. Nicolaus Copernicus, a Polish astronomer, proposed a radical idea: the sun, not Earth, was the center of the solar system. This heliocentric model, published in Copernicus's book De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, challenged the long-held geocentric view and sparked a scientific revolution. Copernicus's model wasn't just a philosophical shift, it offered a simpler and more elegant explanation for the observed motions of the planets. The retrograde motion of planets previously explained by complex epicycles could now be accounted for by the relative motion of Earth and other planets as they orbited the Sun. While Copernicus's model was a significant step forward, it wasn't immediately accepted. It contradicted religious dogma and lacked the observational evidence needed to convince skeptics. Moreover, Copernicus still clung to the idea of circular orbits, which hindered his ability to accurately predict planetary positions. Despite initial resistance, the heliocentric model gradually gained acceptance thanks to the work of astronomers like Johannes Kepler and Galileo Galilei. Kepler refined Copernicus's model by introducing elliptical orbits, while Galileo's telescopic observations provided evidence that supported the heliocentric view. Johannes Kepler, a German astronomer, made groundbreaking contributions to our understanding of planetary motion. His work laid the foundation for modern astronomy and changed the way we perceive our solar system. Building upon Copernicus's heliocentric model and meticulously analyzing the observational data of Tycho Brahe, Kepler formulated his 3 laws of planetary motion. These laws accurately describe the movements of planets around the Sun and have stood the test of time, remaining relevant even in contemporary astronomical studies. Kepler's first law, the law of ellipses, states that planets move in elliptical orbits, with the Sun located at one of the 2 foci of the ellipse. This was a revolutionary idea at the time as it challenged the long-held belief in perfectly circular orbits. This shattered the long-held belief in perfectly circular orbits, which had been the prevailing thought for centuries, dating back to the time of Aristotle and Ptolemy. His second law, the law of equal areas, describes the speed at which planets travel in their orbits. It provides a deeper understanding of the dynamic nature of planetary motion. It states that a line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. This means that the speed of a planet varies depending on its distance from the Sun. This means that planets move faster when closer to the Sun and slower when farther away. This variation in speed was a key insight that helped explain the observed irregularities in planetary motion. Kepler's third law, the law of harmonies, relates a planet's orbital period to its average distance from the Sun. This law provided a clear mathematical relationship that could be used to predict planetary positions. It states that the square of a planet's orbital period is proportional to the cube of its semi-major axis, the average distance from the Sun. This relationship was crucial for the development of celestial mechanics. Kepler's laws provided a precise mathematical framework for understanding planetary motion. They allowed astronomers to predict the positions of planets with great accuracy. They demonstrated that planets don't move at uniform speeds in circular paths, but rather follow predictable elliptical orbits, their speeds dictated by their distance from the Sun. This understanding was a monumental leap forward in the field of astronomy, paving the way for future discoveries and the eventual formulation of Newton's laws of motion and universal gravitation.